Imagine looking up at the night sky, where countless stars twinkle like scattered diamonds, each one a sun, some solitary, others bound together in intricate cosmic dances. But among these celestial partnerships, there's something even more mesmerizing: triple star systems, where three stars orbit one another in a delicate, gravity-defying ballet. These aren't just rare curiosities, they're windows into the universe's most baffling secrets, where the rules of physics twist into shapes we're only beginning to understand. What happens when three stars share the same corner of space? The answers are stranger than fiction, and they're hiding in plain sight, waiting to rewrite everything we thought we knew about how stars live, die, and interact. Picture this: a world with not one, not two, but three suns hanging in the sky, casting ever-shifting shadows as they whirl around one another in an endless game of gravitational tug-of-war. Some of these systems are so chaotic that their stars fling each other into wild, unpredictable orbits, while others settle into rhythms so precise they could be the universe's own clockwork. And here's the thing: these trios aren't just cosmic oddities. They hold clues to some of astronomy's biggest mysteries, from how planets form in such chaotic environments to whether life could exist under three suns. The discoveries scientists have made about these systems sound like they're ripped from the pages of a sci-fi novel, but they're very, very real. That's exactly what we're diving into today: 30 of the most mind-bending, unexpected, and downright bizarre findings about triple star systems. From stars that steal material from one another in a never-ending cosmic heist to bizarre planets that orbit all three suns at once, these revelations will make you question everything you thought you knew about the universe. Some of these systems defy logic, others challenge our understanding of time itself, and a few might even hold the key to unlocking the secrets of dark matter. So buckle up, we're about to take a journey into the heart of some of the universe's most enigmatic stellar families, where the laws of nature dance to a rhythm we're only just beginning to hear. Long before telescopes could pierce the depths of space with the precision we have today, astronomers relying on little more than patience and mathematics stumbled upon something that would upend their understanding of the cosmos. In the early 17th century, the Italian astronomer Galileo Galilei, already famous for proving Earth wasn't the center of the universe, turned his attention to the stars, meticulously recording their movements. But it wasn't until 1640 that the first triple star system was officially recognized, a discovery credited to the Polish astronomer Johannes Hevelius. Using a handmade telescope in his rooftop observatory, Hevelius noticed something peculiar about the star system we now call Polaris, the North Star. At the time, most astronomers believed stars existed either alone or in simple pairs, bound by gravity in predictable orbits, but Polaris shattered that assumption. Here was a system where three stars, not two, orbited one another in a complex gravitational dance. The primary star, Polaris A, was a supergiant, while its two smaller companions, Polaris B and C, circled it in erratic, lopsided paths. This wasn't just unusual, it was thought to be impossible under the prevailing theories of celestial mechanics. How could three massive objects maintain stable orbits without eventually collapsing into chaos or flinging one another into the void? The discovery forced scientists to reconsider everything they knew about gravity and motion. Isaac Newton's laws, which elegantly explained the orbits of planets and binary stars, struggled to account for the delicate balance of a triple system. Some even argued that Polaris must be an optical illusion, a trick of the telescope. But as observations improved, the truth became undeniable. The universe was far stranger than anyone had imagined. What made Polaris even more fascinating was its configuration. Unlike simpler systems where stars orbit in neat, flat planes, Polaris's trio moved in wildly inclined paths, almost as if they were caught in a celestial game of tug-of-war. This hinted at a turbulent past, perhaps a dramatic collision or a near miss with another star system that left its mark. And if one such system existed, astronomers realized there must be others. Polaris wasn't just a curiosity, it was the first clue in a puzzle that would eventually reveal thousands of triple systems, each with its own bizarre story to tell. If you thought having 3 suns in the sky would make planets impossible, think again. Astronomers made a jaw-dropping discovery in 2016 when they found a planet orbiting not 1, not 2, but all 3 stars of the GW Orionis system, a cosmic configuration that defied every expectation. This wasn't just a fluke, it was proof that planets could form and survive in one of the most chaotic environments imaginable. A gravitational battleground where 3 stars constantly pull and twist the fabric of space around them. The star system itself is a spectacle: 2 stars locked in a tight orbit while a third circles them both at a greater distance, creating a celestial merry-go-round of gravitational forces. Amid this turbulence, telescopes spotted a massive planet, likely a gas giant several times the size of Jupiter, carving its path through the swirling debris. What's staggering is how it got there. Planets typically form in flat, orderly disks of dust and gas around young stars. But in a triple system, the gravitational tug of war warps these disks into misaligned, wobbly rings, like a record spinning off kilter on a turntable. Scientists expected this chaos to prevent planet formation altogether. Yet there it was, a planet that shouldn't exist, thriving in the madness. This discovery flipped the script on habitability, too. If a gas giant can form here, could rocky, Earth-like planets also emerge in such systems? Imagine a world where the horizon is lit by 3 suns, casting ever-changing patterns of light and shadow. The habitable zone, the region where liquid water could exist, becomes a moving target, stretching and shifting as the stars dance. Some triple systems might even offer more stable conditions than binaries, with one star dominating the others and creating pockets of relative calm. But the real kicker: life. While the constant light and gravity shifts would make survival a challenge, some organisms on Earth thrive in extreme environments: deep sea vents, acid lakes, even the vacuum of space aboard the International Space Station. If life can adapt there, why not under 3 suns? The discovery of planets in triple systems doesn't just expand the map of where we might find alien life, it redraws it entirely. Suddenly, the most exotic corners of the galaxy are back on the table, proving once again that the universe loves to surprise us. Now imagine a cosmic stage where stars don't just orbit each other, they perform. In one remarkable triple system, the stars align so perfectly from our vantage point on Earth that they eclipse one another like clockwork, casting shadows across the galaxy. This isn't just a celestial light show, it's a goldmine for astronomers. Every time one star passes in front of another, it dims the system's light in a unique pattern, revealing secrets about their sizes, temperatures, and even the turbulent winds raging between them. Take the system TIC 1687984 for example. Here, 3 stars, 2 locked in a tight embrace and a third circling farther out, cross paths so precisely that they create a rhythmic flickering, like a lighthouse beam cutting through fog. When the smallest star slides behind one of its larger siblings, the dip in brightness tells scientists exactly how big it is. When the largest star eclipses another, the way light filters through its outer atmosphere exposes its chemical makeup. These eclipses happen like cosmic clockwork, some every few days, others over weeks, painting a dynamic portrait of stellar dance. But the real magic lies in the unexpected. Sometimes the eclipses don't play out as predicted. A slight delay, an extra wobble, these anomalies hint at unseen forces. Maybe an undiscovered planet tugs at the stars, or perhaps the stars themselves warp space-time with their gravity. Each irregularity is a breadcrumb leading to deeper mysteries. And because the stars are so close, their gravitational pull stretches them into egg-shaped distortions, creating tides of superheated plasma that surge between them. This rare alignment isn't just scientific luck, it's a controlled experiment written into the fabric of the universe. By studying these eclipses, astronomers can measure stellar masses down to a fraction of a percent, test theories of gravity under extreme conditions, and even probe how stars exchange material in a cosmic game of hot potato. The data is so precise that it's like watching these stars through a magnifying glass. Every flicker, every shudder, every stolen breath of light tells a story. And here's the kicker: systems like this might be more common than we thought. As telescopes grow sharper, astronomers are spotting these eclipsing trios hidden in plain sight, their secrets waiting to be unlocked with every passing shadow. It's a reminder that sometimes the universe doesn't just whisper its secrets, it flashes them in strobe lights, if only we know where to look. Just when we thought triple star systems couldn't get any stranger, astronomers stumbled upon a cosmic nightmare, a trio where one of the members isn't a star at all but a black hole. This system, known as HR 6819, lurks around 1,000 light-years from Earth, making it one of the closest black holes ever discovered. And its existence rewrites what we thought we knew about how these invisible monsters form. The discovery hinged on a telltale wobble. Using the European Southern Observatory's Very Large Telescope, scientists tracked two visible stars orbiting each other at breakneck speed, completing a full dance every 40 days. But something was off. Their motion had an unnatural hitch, as if an unseen hand were tugging at them. That ghostly pull could only mean one thing: a third object, invisible yet weighing in at around 4 times the mass of our Sun, was hiding in the shadows. Further analysis confirmed the terrifying truth: this wasn't a dim star or a rogue planet. It was a black hole, silently feasting on nothingness while its stellar companions whirled around it. What makes this system so revolutionary isn't just the black hole's presence, it's how ordinary the rest of the system appears. Most black holes we've found are in violent, high-energy environments, like the centers of galaxies, or paired with stars they're actively devouring. But HR 6819's black hole is dormant, a sleeping giant that hasn't consumed material in millennia. This suggests something startling. Black holes might form quietly, without the dramatic supernova we've long assumed were their birthright. Even more bizarre is how calm the system seems. The two visible stars show no signs of distress, no swirling accretion disks, no violent X-ray bursts. It's as if they don't even realize their sibling is a cosmic predator. That tranquility hints at a hidden population of similar systems, where black holes blend in among ordinary stars, undetected until their gravity gives them away. If this one slipped under our noses for so long, how many others are out there, lurking in plain sight? This discovery forces us to rethink the life cycles of stars. Maybe black holes don't always form in catastrophic explosions. Some might collapse quietly, like a building imploding in on itself, leaving behind no fireworks to mark their passing. And if that's true, the universe could be teeming with these invisible ghosts, woven into the fabric of star systems we thought we understood. HR 6819 isn't just a curiosity. It's a cosmic wake-up call, reminding us that the darkest secrets often hide in the least expected places. Some stars don't just dance, they race. Deep in the constellation of Orion, astronomers have clocked a triple star system moving at speeds that defy common sense, where stellar bodies whip around each other so fast they complete an entire orbit in less time than it takes Earth to circle the Sun once. This system, named TSE 278899596, holds the current record for the fastest known triple configuration, with its innermost stars completing their frantic waltz every 1.4 days. That's 300 times faster than Mercury orbits our Sun. The physics behind this speed demon is both elegant and terrifying. Each star's gravity pulls on the others with such intensity that they're practically skimming each other's surfaces, their outer atmospheres stretched into teardrop shapes by tidal forces. At these distances, relativity isn't just a theory, it's a daily reality. Time itself flows slightly slower for these stars compared to the rest of the universe, an effect predicted by Einstein but rarely seen so dramatically in nature. The system's breakneck speed also means its stars aren't the serene spheres we often imagine. Instead, they're seething cauldrons of plasma, their surfaces roiled by constant gravitational kneading, sparking solar flares that would dwarf anything our sun has ever produced. But such intensity comes at a price. Calculations show these stars are locked in a death spiral, their orbits gradually decaying as they bleed energy in the form of gravitational waves, ripples in space-time first detected by LIGO in 2015. In about 300,000 years, a blink in cosmic terms, the two closest stars will merge catastrophically, likely triggering a supernova or birthing a neutron star. The third star, currently orbiting at a safer distance, will either be flung away like a cosmic slingshot or become trapped in an even more bizarre configuration, orbiting the leftover stellar corpse. What's truly mind-bending is how common this might be. Current models suggest up to 1 in 5 triple systems could host such extreme inner pairs, their frenzied orbits hidden by the glare of their common siblings. These speedster trios challenge our understanding of stellar evolution, proving that stars can exist at least for a while in configurations once thought physically impossible. They're cosmic time bombs ticking away at impossible speeds, rewriting the rules of celestial mechanics with every dizzying revolution. Among the strangest cosmic ballets ever witnessed is a triple star system where two of the dancers move so close together they share the same shroud of gas, like celestial twins wrapped in a single searing blanket. Astronomers call this phenomenon a contact binary, but in the system HD 188753, it's taken to an extreme even experts couldn't predict. Here, two stars orbit so tightly that their outer atmospheres have merged into a single, roiling envelope of superheated plasma, while a third star circles them at a safer distance, watching the chaos unfold. This isn't just a case of stars brushing against each other. The two inner stars are so deeply entwined that material constantly flows between them, creating a shared ecosystem of matter and energy. Imagine two whirlpools spinning in the same bathtub, their currents colliding and mingling until it's impossible to tell where one ends and the other begins. This cosmic tango generates staggering temperatures up to 50,000 degrees Celsius in the turbulent boundary layer where their atmospheres clash. The friction here sparks violent stellar winds and magnetic storms, launching loops of plasma far into space like celestial lightning. What makes this system truly bizarre is how it defies the usual fate of such close encounters. Normally, stars sharing an atmosphere would spiral inward and merge in a cataclysmic explosion. Yet somehow, these two have maintained their delicate balance for millions of years, possibly stabilized by the gravitational influence of their distant third companion. This outlier challenges our models of stellar evolution, suggesting that under the right conditions, stars can exist in a kind of suspended animation, neither fully separate nor fully merged. The repercussions ripple far beyond this one system. If stars can share atmospheres long-term, it raises wild questions about how they evolve. Could such binaries delay their inevitable collisions indefinitely? Might they forge exotic stellar hybrids, their cores fusing elements in ways never before seen? And what does this mean for planets forming in their vicinity, bathed in the unpredictable radiation of two stars breathing as one? HD 188753 doesn't just offer a spectacle, it's a living laboratory, testing the limits of what stars can endure. Astronomers have a name for celestial objects that break all the rules. They call them impossible stars. And in the constellation of Scorpius, there's a triple star system that fits that description perfectly. Officially catalogued as HD 135344, This trio of young, hot stars shouldn't exist according to every major theory of stellar formation. The problem, they're too close, too massive, and orbiting in a geometry that physics says should have torn them apart before they ever finished forming. Picture a stellar nursery, a dense cloud of gas and dust where stars are born. Current models predict that when multiple stars form together, they either settle into wide, stable orbits or collide catastrophically. But HD 135344 laughs in the face of these predictions. Here, three massive stars, each 20 times heavier than our Sun, are crammed into a space smaller than Earth's orbit around the Sun. The two inner stars complete a full revolution every 2.7 days, while the third loops around them in an oval-shaped path that shouldn't remain stable for more than a few thousand years. Yet somehow, this system has persisted for millions. The mystery deepens when you examine their chemistry. Normally, stars born together share nearly identical compositions, like siblings raised in the same home. But spectroscopic analysis revealed these three have wildly different amounts of elements like oxygen and carbon, as if they were strangers thrown together by cosmic chance. One leading theory suggests this system wasn't born in a single collapse of a gas cloud, but formed through a series of unlikely gravitational captures, like a stellar game of musical chairs where the music stopped at just the right moment. Even more perplexing is what this means for planet formation. The gravitational turbulence in such a tight system should have prevented any planets from coalescing, yet observations hint at debris disks, the raw material for worlds still clinging to the chaos. If planets can form here, it rewrites the playbook on where life might take root in the universe. HD 135344 doesn't just challenge our models, it forces us to consider that stars might assemble in ways we've never dared imagine, through processes so rare we've yet to witness them elsewhere in the cosmos. Most star systems follow a simple rule, like attracts like. Stars of similar size, temperature, and age tend to cluster together, bound by gravity in harmonious orbits. But in the depths of the Milky Way, astronomers found a system that breaks every convention, a trio of stars so different from one another. It's as if the universe assembled them from spare parts. Meet HD 131399, where the surface temperatures of its three stars range from a searing 35,000 degrees Celsius to a relatively chilly 3,500. That's the difference between a blowtorch and a campfire, all dancing in the same gravitational embrace. How does such a mismatched family even form? The answer lies in a cosmic game of capture. The hottest member, a blue-white behemoth, likely formed first from a collapsing cloud of gas, its intense radiation blowing away nearby material. Millions of years later, two smaller stars, a yellow sun-like star and a ruddy red dwarf, drifted close enough to be snared by its gravity. The system's unusual architecture supports this. The blue star sits at the center, while the cooler pair orbit at a distance, their paths stretched into elongated ellipses by the uneven gravitational tug of war. But the real shocker is what's happening between them. The blue star's fierce ultraviolet radiation is literally stripping atoms from the red dwarf's atmosphere, creating a glowing bridge of ionized gas that arcs between them. Meanwhile, the yellow star orbits just far enough to avoid this fate, basking in the blue star's light like a planet caught in perpetual daylight. This three-way interplay creates a laboratory for studying stellar evolution under extreme conditions. The red dwarf, though the smallest, may actually be the oldest, its cooler temperature suggesting it's been burning fuel slowly for billions of years, while its blazing sibling races through its life at breakneck speed. What does this mean for potential planets? Any world forming here would face an environmental roller coaster. Days might alternate between scorching ultraviolet blasts from the blue star and gentler warmth from the others, with seasons changing not by axial tilt but by which star dominates the sky at a given moment. Yet somehow, against all odds, astronomers have detected traces of a debris disk, a ring of dust and rock that could one day coalesce into planets. If worlds can form in this stellar pressure cooker, it forces us to redefine what habitable really means. HD 131399 doesn't just challenge our ideas about star formation, it proves the universe has a flair for dramatic contrasts, binding together cosmic opposites in a dance that defies all expectation. Gravity isn't always the glue that holds star systems together. Sometimes it's the force that tears them apart. In the constellation of Cygnus, astronomers have identified a triple star system locked in a slow-motion breakup, where one star is being violently evicted from its cosmic family. This system, catalogued as HD 65029, consists of 3 stars born together, but unlike most stable trios, their orbits resemble a game of musical chairs where one participant is about to be flung into the void forever. The drama unfolds like this. 2 of the stars, a close-knit binary pair, circle each other at a relatively safe distance, while the third star loops around them in an increasingly erratic path. Every time this outsider swings close, the binary stars yank it with their combined gravity, stealing a fraction of its momentum. Over thousands of years, these repeated gravitational tugs have stretched the third star's orbit into a teardrop shape, accelerating it toward escape velocity. Current measurements show it's already traveling at nearly 12 kilometers per second, too fast to remain bound to the system indefinitely. Within 500,000 years, it'll break free entirely, becoming a rogue star adrift in interstellar space. What makes this discovery so valuable isn't just the spectacle, it's the snapshot it provides of a critical phase in stellar evolution. Most triple systems we observe are either stable or already reduced to binaries after a violent ejection. HD 65029 is caught in the act, offering a rare chance to study the mechanics of stellar divorce. The process isn't clean. As the third star struggles against its fate, its gravity warps the orbits of the remaining pair, nudging them closer together. By the time the ejection completes, the binary will be tighter and faster orbiting than before, its stars destined to eventually merge in a fiery collision. This system also solves a long-standing mystery: why our galaxy is filled with solitary runaway stars hurtling through space at unnatural speeds. Astronomers had theorized that many were expelled from unstable multiples, but HD 65029 provides the smoking gun, a system actively generating one of these cosmic fugitives. The ejected star won't go gently. As it departs, simulations show it may rip away traces of the system's protoplanetary debris, scattering comets and asteroids like confetti in its wake. Any planets that formed here would face apocalyptic upheaval, their orbits scrambled or their atmospheres stripped by the departing star's gravity. Yet the most tantalizing lesson lies in the timing. The fact that we're witnessing this ejection now suggests such events might be far more common than assumed. If 1 in every few hundred triple systems is actively expelling a member, it could mean thousands of stars in our galaxy alone were once part of larger families before gravity tore them apart. HD 65029 isn't just a curiosity, it's a cosmic autopsy, revealing the violent processes that shape the stellar population around us. And somewhere out there, another trio is already beginning its own slow, inevitable unraveling. Some triple star systems move to a rhythm that makes no sense at all, their orbits twisting through space like tangled yarn, rather than the neat ellipses we've come to expect. Take the system LTT 1445, where the stars don't just circle one another in flat, predictable planes. Instead, they carve paths so tilted and warped, it's as if gravity itself gave up trying to impose order. Here, the 3 stars orbit at wildly different angles, their trajectories crisscrossing like drunken fireflies, defying every model of stable celestial motion. What makes this possible? Chaos theory in action. Normally, multi-star systems settle into what astronomers call coplanar orbits, where all stars move roughly in the same flat disk, much like planets around our Sun. But LTT 1445 stars operate in three separate planes, each tilted by up to 60 degrees relative to the others. This creates a gravitational free-for-all, where the pull of one star can suddenly yank another off course, sending it veering into a new trajectory. The innermost pair whip around each other every 5 days, while the third star loops them on a stretched, off-kilter path that takes years to complete. The real mystery is how such a system survives without tearing itself apart. Simulations show these extreme orbits shouldn't last. Stars this misaligned should either collide, eject one another, or settle into a comma configuration within a few million years. Yet LTT 1445 has persisted for an estimated billion years, suggesting some unseen mechanism keeps it balanced. One theory points to the star's masses being perfectly mismatched. The gravitational push and pull between them might create accidental stability zones, like a spinning top that wobbles but never falls. But the implications stretch far beyond this one oddball system. If triple stars can thrive in such extreme arrangements, it forces us to reconsider how common or rare planets might be in these environments. A planet orbiting one star would experience gravity constantly shifting direction as the other stars pass by at bizarre angles, potentially destabilizing its climate or even kicking it out of orbit altogether. Yet some researchers argue these chaotic systems could also create temporary, sweet spots, pockets of calm where a planet might enjoy stable conditions for long stretches. Even stranger, similar systems have been spotted with planets still clinging to existence. This raises a tantalizing possibility. Maybe life doesn't need the quiet predictability of a single star system. Perhaps in the universe's most chaotic neighborhoods, there are worlds that have learned to adapt where life, if it exists, has evolved under skies where the suns rise in unpredictable directions, casting ever-changing shadows. LTT 1445 isn't just breaking the rules, it's rewriting them, proving that when it comes to star systems, the universe has a flair for the dramatic. Deep within the Orion Nebula, where newborn stars blaze through veils of cosmic dust, astronomers have spotted something extraordinary, a triple star system so young, its stars are practically still breathing their first stellar breaths. Designated as object name pending, this trio is the youngest multiple star system ever observed, estimated to be less than 100,000 years old. That's a cosmic infant, barely a blink in the universe's timescale, and its discovery is rewriting textbooks on how stars are born together. What sets this system apart isn't just its age. It's the way these stars are still wrapped in the remnants of their birth cloud, like chicks nestled in a fractured eggshell. The primary star, already shining fiercely, is flanked by two smaller siblings, all three connected by twisting filaments of gas that pulse with the raw energy of their formation. High-resolution radio images reveal how gravity carved this system into existence. The original gas cloud fragmented unevenly, collapsing into three dense knots that ignited into stars at slightly different times. The smallest star, still gathering mass, is actively funneling material from a jagged disk of debris, while the largest has already begun blowing away its natal cocoon with searing stellar winds. But the real revelation lies in their orbits. Unlike older triple systems where gravity has had time to tidy things up, these stars are caught in a gravitational tug of war that mirrors the chaos of their birth. They whirl around one another in lopsided, unstable paths, their motions more like a stumbling dance than the precise orbits of mature systems. One star loops far out, only to be yanked back by its siblings' combined pull, while the innermost pair spirals so close that their magnetic fields tangle, sparking arcs of plasma visible in ultraviolet light. This turbulent arrangement suggests a shocking truth. Triple systems might not form neatly from symmetrical collapse, but through a messy, almost competitive process where stars steal material from one another even as they're being born. The implications ripple far beyond this one system. If this is how most triples start, it means the universe favors drama from the very beginning, stars elbowing for space, warping their shared cradle into bizarre shapes, and settling into unstable configurations that only time can smooth into order. It also raises tantalizing questions about planets. Could worlds form in such chaos, or does the violence of youth make these systems planetary dead zones? Early data hints at dust rings around the largest star, though whether they'll survive long enough to coalesce into planets is anyone's guess. For astronomers, this system is like catching a supernova in the act, a rare peek at a fleeting moment in stellar evolution. Most triple systems we study have aged past their turbulent infancy, their origins smoothed by time. But here, we're witnessing the cosmic equivalent of a nursery brawl, where the rules of gravity are still being written in real time. And if this is how one system forms, how many others out there are being born in the same wild way, their stars fighting for dominance even as they ignite? The answer could reshape our understanding of stellar families and prove that when it comes to star formation, chaos isn't just possible, it's the norm. Some triple star systems hide more than meets the eye, like the curious case of KY 5620, where astronomers detected a fourth object lurking in the shadows, bending the paths of its stellar neighbors in ways no one could explain. At first glance, this system appeared ordinary, three stars locked in a complex dance, with two orbiting tightly while a third circled farther out. But meticulous observations revealed something unsettling. The stars' orbits wobbled unpredictably, as if an unseen hand were nudging them off course. The culprit, either a rogue planet the size of Jupiter gone astray or something far stranger, a failed star known as a brown dwarf lurking just beyond detection. The evidence came from minute timing variations. When one star eclipsed another, the event arrived milliseconds late, then early, as if an invisible mass were tugging the system's center of gravity back and forth. Calculations suggested an object roughly 40 times heavier than Jupiter, too massive to be a planet, yet too small to ignite as a full-fledged star. Brown dwarfs occupy this cosmic gray area, and if confirmed, this would be the first discovered in such a tight triple-star arrangement. But the plot thickened when alternative models suggested a different scenario. A free-floating rogue planet, ejected from some distant system and captured by KY 5620's gravity, now haunting its outskirts like a celestial ghost. What makes this mystery so compelling is how it challenges our understanding of cosmic neighborhoods. Conventional wisdom says triple systems are chaotic enough without adding interstellar interlopers. Yet here, the data suggests either a brown dwarf formed alongside these stars, defying models that say such objects rarely survive in multi-star environments, or a planet hurled into exile found refuge here against all odds. Both possibilities rewrite the rules. If it's a brown dwarf, its mere existence implies these failed stars might be hiding in plain sight throughout the galaxy, gravitationally tethered to systems we thought we understood. If it's a rogue planet, it proves such worlds don't always drift alone. Sometimes they crash the party. The implications ripple outward. A captured planet could carry remnants of its birth system ices, organics, even traces of a lost atmosphere, offering a snapshot of a world we'd never see otherwise. A brown dwarf, meanwhile, might harbor bizarre weather patterns with molten iron rain and storms powered by internal heat rather than sunlight. Future telescopes could settle the debate, but for now, KY 5620 keeps its secret. It's a reminder that even systems we've studied for years can harbor shadowy guests, cosmic stowaways rewriting the story of how star systems form, evolve, and occasionally adopt strays. Most stars burn with a steady glow, their colors constant across millions of years, but in the cosmos there are always exceptions. Take the system HD 5980, where the night sky wouldn't just have three suns, it would shift hues like a celestial mood ring. This triple system doesn't just combine light, it transforms it, creating an otherworldly display where the dominant color changes based on which star takes center stage in their endless orbital dance. At the heart of this phenomenon are the star's wildly different temperatures. The primary star is a blue giant, blazing at over 30,000 degrees Celsius and flooding space with harsh ultraviolet light. Its closest companion is a yellow star similar to our Sun, while the third member is a dim red dwarf, barely hot enough to glow visibly without assistance. As they orbit, their relative positions shift, and from a distance their combined light blends like paints on a cosmic palette. When the blue star dominates the alignment, the system gleams an eerie azure. As the yellow star swings forward, the tone warms to golden, and when the red dwarf's faint glow gets its moment, the entire system dims to a deep, ruddy crimson. What makes this color shift so dramatic isn't just the stars' differences, it's their orbits. Unlike most triples where stars move in predictable, spaced-out patterns, HD 5980's members follow tight, overlapping paths that amplify the visual effect. The blue and yellow stars complete a full orbit every 18 days, their rapid dance ensuring the hue changes are noticeable even across human timescales. Meanwhile, the red dwarf's slower, wider path means its influence waxes and wanes over months, adding a long-term rhythm to the kaleidoscope. This isn't just a pretty light show, it's a goldmine for astronomers. By measuring the precise timing of these color shifts, scientists can map the star's orbits down to the kilometer, something nearly impossible with static systems. The changes also reveal details about each star's atmosphere. As one passes in front of another, filters of different wavelengths expose hidden layers of their chemistry. For instance, the blue star's fierce radiation strips atoms from the red dwarf's outer layers, creating a glowing halo of hydrogen that tints the system violet during certain alignments. The implications stretch beyond this one trio. If color-changing systems are common, and recent surveys suggest they might be, they could explain strange observations of distant galaxies where some clusters flicker in ways single stars never could. They also raise wild questions about potential planets. Imagine a world where seasons aren't marked by temperature, but by the sky's hue shifting from gold to blue to blood red as its suns realign. Photosynthetic life here would face an evolutionary roller coaster, adapting to wavelengths that change over lifetimes. HD 5980 doesn't just dazzle, it reminds us that the universe's artistry isn't confined to stillness. Sometimes the most breathtaking masterpieces are the ones that never stop moving. In the cosmic dance of triple star systems, few phenomena are as mesmerizing or as destructive as the way stars can steal life from one another. The system Beta Lyrae offers a front-row seat to this stellar vampirism, where three stars are locked in a gravitational embrace so intimate that they're constantly trading mass like celestial thieves. Here, the largest star, a blue giant, is being slowly devoured by its smaller but greedier companion, while a third star watches from a distance, its own fate hanging in the balance. The process begins with proximity. The two inner stars orbit so close that their outer atmospheres touch, creating a bridge of superheated gas between them. The more massive star, though larger, has aged faster, expanding into a bloated giant with a gravity too weak to hold onto its outer layers. Its smaller neighbor, younger and denser, siphons this material away at a rate equivalent to losing an Earth's worth of mass every year. The stolen gas doesn't just vanish, it spirals onto the smaller star in a glowing accretion disk, heating up to millions of degrees and emitting violent X-ray flares visible across the galaxy. But the real twist lies in how this theft alters their evolution. Normally, massive stars burn bright and die young, exploding as supernova within millions of years. Yet as the blue giant loses mass, it's effectively dieting, extending its lifespan by shedding the fuel that would have doomed it. Meanwhile, the thief star grows unnaturally heavy, its core pressure skyrocketing until it risks collapsing prematurely into a neutron star. It's a cosmic paradox. The victim star might outlive its predator because of the very act that's consuming it. The third star adds another layer of chaos. Though distant enough to avoid direct mass theft, its gravity tugs on the inner pair, warping their orbits and occasionally funneling extra material toward the accretion disk. Simulations show this interference creates bursts of erratic transfer, periods where the rate of stolen mass spikes tenfold, triggering outbursts bright enough to outshine the combined system for weeks. What does this mean for the system's future? Astronomers predict the two inner stars will eventually merge, igniting a temporary red nova visible to the naked eye from Earth. The resulting megastar, bloated with mixed material from both predecessors, could defy classification, neither a true giant nor a main sequence star, but something entirely new. As for the third star, its fate hinges on the merger's violence. It might be ejected entirely or drawn closer to become part of an even stranger binary. Beta Lyrae isn't just a spectacle, it's a time-lapse of stellar evolution playing out in real time. Most stars live too slowly for us to witness their life cycles, but here the clock is sped up by gravitational mayhem. With every stolen breath of gas, these stars rewrite their destinies, proving that in the cosmos, even the act of dying can be a collaborative or predatory art. Among the most extreme laboratories in the universe, few can rival the bizarre triple system PSRJ 0337 plus 1715, a cosmic oddity where one of the stars is a pulsar, spinning at nearly 366 times per second while being tugged by two white dwarf companions. This isn't just a rare configuration, it's a natural experiment for testing Einstein's theory of general relativity with precision impossible to replicate on Earth. Pulsars, the ultra-dense, rapidly spinning remnants of supernova explosions, act like cosmic lighthouses, emitting beams of radiation that sweep across space with metronomic regularity. Even the slightest gravitational disturbance alters their rhythm, and in this system, the pulsar's ticks arrive with variations so subtle they reveal the intricate dance of all three stars. The two white dwarfs orbit close enough to warp space-time around them, creating ripples that delay or accelerate the pulsar's signals by microseconds, a phenomenon called the Shapiro time delay. These minute distortions allow astronomers to map the system's gravity field in exquisite detail, confirming predictions Einstein made a century ago. But the real test lies in how the stars move. General relativity dictates that massive objects in tight orbits should spiral inward as they lose energy through gravitational waves. In most systems, this effect is too gradual to measure, but here, the pulsar's precision acts like a stopwatch tracking the decay. Sure enough, the orbits are shrinking at exactly the rate Einstein's equations predict, down to a fraction of a millimeter per year. This level of confirmation is unprecedented. It's like weighing a feather on a planetary scale and getting the answer right to the trillionth decimal place. What makes this trio even stranger is how it formed. Pulsars usually emerge from violent supernova, yet these explosions typically kick their remnants clear of any companions. The fact that this pulsar retained two stars suggests its birth was unusually gentle. Perhaps the supernova was asymmetric, leaving the system intact. Alternatively, the white dwarfs might have been captured later, though simulations show that statistically improbable. Either way, their survival challenges our understanding of stellar death and rebirth. Beyond testing relativity, this system holds clues to dark matter. If unseen mass were lurking nearby, its gravity would subtly alter the pulsar's timing in ways ordinary matter can't explain. So far, no such anomalies exist, ruling out certain dark matter candidates in this corner of the galaxy. It's a reminder that sometimes the universe's strangest arrangements aren't just curiosities, they're tools honed by chance to reveal truths hidden in the fabric of reality itself. Most planets in triple star systems face a brutal fate, either flung into the void or torn apart by gravitational chaos. but astronomers have uncovered a rare exception, the KIC 8561309 system, where multiple planets orbit all three stars in perfect alignment, as if defying the mayhem around them. These worlds didn't just survive the turbulence, they mastered it, carving paths so precise they could teach a masterclass in cosmic balance. The secret lies in an unexpected harmony. While the three stars, two locked in a tight binary and a third orbiting farther out, wreak havoc on most trajectories, their combined gravity creates narrow, sweet spots where planets can stabilize. Think of it like threading a needle while riding a roller coaster. The planets here occupy orbits perpendicular to the star's plane, minimizing disruptive tugs. Every time the binary stars whip around each other, their gravitational kicks cancel out over time, thanks to a phenomenon called orbital resonance. It's as if the star's chaos accidentally builds a safety net for worlds caught in the crossfire. One planet in this system, dubbed Kepler 4-5b, exemplifies this delicate dance. Observations show it circles all three stars every 187 days, its path tilted just enough to avoid the worst gravitational shoves. The star's competing pulls even out over its orbit, creating pockets of stability where, against all odds, seasons could be milder than Earth's. But the real marvel is its longevity. This planet has likely maintained its orbit for billions of years, outlasting violent phases of stellar youth when its stars flared and ejected rogue comets by the thousands. What's even wilder, this isn't the only system where planets buck the trend. In HD 131399, a gas giant orbits so neatly aligned with its three suns that its shadows cast perfect triple eclipses on hypothetical moons. Simulations suggest these worlds formed differently than planets in calm systems. Instead of coalescing from serene disks, they might emerge from warped, twisted rings of debris that somehow find order in the chaos. The implications are staggering. If planets can thrive here, the galaxy's habitable zones might extend far beyond single-star systems. Imagine a world where three sunrises paint the sky in shifting hues, yet the climate remains stable enough for liquid water and maybe life. These aligned orbits aren't just flukes, they're proof that even in the universe's most chaotic neighborhoods, nature finds a way to write its own rules. And somewhere out there, another triple-star planet might be waiting, its skies filled with sunlight from multiple angles, its existence a testament to gravity's hidden harmonies. Some stars don't just shine, they flicker, pulse, and deceive. Among the most puzzling of these cosmic chameleons is the triple system VV Cephei, where three stars conspire to create a light show so erratic, it tricked astronomers into classifying it as a single, bizarre variable star for decades. At first glance, the system's brightness swings followed patterns typical of pulsating giants, dimming and flaring over predictable cycles. But beneath the surface, the truth was far stranger. These weren't the rhythms of one star, but the combined illusion of three stellar actors performing in perfect gravitational sync. The key to the mystery lies in their orbits. The primary star, a monstrous red supergiant, dwarfs its two smaller companions, a blue main sequence star and an enigmatic, faint third partner. Every 20 years, the blue star plunges so close to the red giant that it vanishes entirely behind its swollen outer layers, causing the system's light to plummet by nearly 70%. Meanwhile, the third star's distant but precise orbit adds its own subtle beats, brightening the system at irregular intervals as its gravity tugs streams of gas from the others, sparking temporary flares. The result, a light curve so complex, early observers catalogued it as an irregular variable, never suspecting multiple stars were behind the masquerade. What makes VV Cephei truly exceptional is how it exploits stellar teamwork to mimic solitary chaos. Most variable stars change brightness due to internal processes, expanding and contracting as their nuclear furnaces stutter. Here, the variations arise entirely from celestial geometry, eclipses, tidal distortions, and stolen gas igniting in unpredictable bursts. The red giant's atmosphere alone is a stage for drama. so vast and diffuse that the blue star orbits inside it for months at a time, surfing a sea of superheated plasma that glows differently depending on how deeply it's submerged. Modern telescopes finally unraveled the deception by catching the system mid-eclipse, spotting the blue star's light flickering like a candle behind the red giant's smoky veil. Spectroscopy revealed even more clues, distinct chemical signatures from all three stars, each contributing its own spectral line that shifted as they moved. Suddenly, the variable star was unmasked as a gravitational tango, its light changes not random but choreographed with pinpoint precision. This discovery reshaped how astronomers interpret other erratic variables. If VV Cephei could hide its triple identity for so long, how many more lonely variables might actually be stellar teams in disguise? Surveys now actively hunt for hidden companions in similar systems, and the findings are startling. Up to 1 in 5 irregular variables may owe their quirks to unseen stellar partners. VV Cephei doesn't just challenge our classifications, it reveals how easily the universe fools us when stars work together, their combined light painting illusions across the cosmos. Stellar cannibalism sounds like something out of a cosmic horror story, but in the triple system T Coronii Borealis, it's playing out in real time. Here, a white dwarf, the dense, Earth-sized corpse of a dead star, is locked in a slow-motion feast, stripping hydrogen from its bloated red giant companion like a celestial parasite. Every few decades, this stolen material builds up on the white dwarf's surface until it ignites in a runaway thermonuclear explosion, temporarily making the system one of the brightest points in the night sky. But the real shocker, the third star, a quiet red dwarf orbiting farther out, is silently shaping this deadly dance with its gravity, ensuring the carnage continues on a predictable schedule. This gruesome stellar buffet tells us something profound about how stars die. Normally, red giants shed their outer layers peacefully, creating beautiful planetary nebulae. But when a hungry companion is present, the process turns violent. The white dwarf in T Coronii Borealis doesn't just steal gas, it corrupts it. As hydrogen accumulates on its surface, pressures and temperatures soar until fusion ignites explosively, mimicking the birth of a new star for a few fleeting days. These nova outbursts should eject all the stolen material back into space, but observations reveal a sinister twist. The white dwarf holds onto some of it, growing denser with each cycle. Over millennia, this could push it past a catastrophic threshold, triggering a supernova that obliterates the entire system. The red dwarf's role in this drama is equally fascinating. Though distant, its gravity subtly tugs on the inner binary pair, stabilizing their orbits just enough to keep the cannibalistic cycle regular. Without this unseen referee, the white dwarf and red giant might spiral into chaos long before reaching their explosive finale. It's a cosmic balancing act, one that offers a rare window into how multi-star systems can prolong stellar lives or hasten their deaths. Astronomers call these arrangements cataclysmic variables, but T Coronii Borealis stands out for its sheer predictability. Most nova erupt randomly, yet this system has flared like clockwork every 80 years since its discovery in 1866. With the next explosion expected as early as 2024. That reliability lets scientists study stellar cannibalism in unprecedented detail, from the physics of hydrogen theft to the shockwaves that ripple through the surrounding space. What's most unsettling is how common this might be. Recent surveys suggest up to 1/3 of white dwarfs in triple systems could be quietly feeding on their neighbors, biding time until their next explosive meal. Some may even be invisible to us, their outbursts too faint or their orbits misaligned, leaving their crimes undetected. T Coronii Borealis isn't just a spectacle, it's a warning. Behind the serene twinkle of the night sky, some stars aren't just dancing, they're dining. Physics textbooks tell us that stable star systems follow certain rules, that gravity should keep orbits predictable, that chaos eventually settles into patterns. But in the depths of the Milky Way, there's a triple star system that scoffs at these assumptions. Designated as HD 18689, this trio of stars moves in orbits so bizarre they've ignited a firestorm among astronomers, because according to our best models, this system shouldn't exist at all. The problem starts with their paths. The two inner stars, both sun-like in size, whip around each other in a perfect circle every 9 days, normal enough. But the third star, slightly smaller, loops around them in an orbit so stretched it resembles a spaghetti strand tossed into space. At its closest approach, it veers near enough to skim the inner pair's gravitational field, then catapults outward to a distance 16 times farther than Pluto is from our Sun. This extreme oval-shaped path, known as an eccentric orbit, defies all expectations for long-term stability. Simulations show such lopsided arrangements should self-destruct within a few million years, yet spectroscopic dating reveals HD 18689 has maintained this madness for over a billion. The debate centers on how this imbalance persists. One camp argues the system must be younger than it appears, its orbits artificially extended by some recent disturbance, perhaps a close encounter with another star or rogue planet. Others propose a radical alternative, that an unseen fourth object, maybe a black hole or dense neutron star, lurks just beyond detection, its gravity shepherding the outer star's path like an invisible leash. The most controversial theory, that we're witnessing a rare gravitational resonance, where the star's pulls accidentally synchronize in a way that counteracts chaos, like three pendulums on a shared string finding an unexpected rhythm. Clues hide in the star's chemistry. The outer star shows abnormal traces of lithium, an element usually destroyed early in a star's life, suggesting it might be a captured wanderer adopted into the system after forming elsewhere. If true, its wild orbit could be a temporary fluke, a celestial intruder still settling into its new home. But that raises another puzzle. Why haven't the inner stars ejected it yet? Their combined gravity should have flung it into interstellar space eons ago. For now, HD 18689 keeps its secrets, its stars tracing their impossible paths like rebellious dancers ignoring the choreography. Every new observation deepens the mystery, proving that sometimes the universe isn't just stranger than we imagine, it's stranger than we can imagine. And if one system laughs at the rules, how many others are out there, quietly rewriting physics in the cosmic dark? Most stars shine with visible light, but in the system Centaurus X3, the real spectacle happens in wavelengths human eyes can't see, where three stars conspire to blast the cosmos with some of the most intense X-rays ever detected. This isn't just a stellar trio, it's a cosmic particle accelerator where gravitational forces and stellar vampirism collide to create energies that defy imagination. At the heart of this system lies a neutron star, the crushed core of a dead star so dense a teaspoon of its material would weigh 1 billion tons. It orbits a blue supergiant so massive its gravity strips away entire layers of the star's atmosphere, funneling gas onto the neutron star's surface at nearly half the speed of light. The impact is apocalyptic. As this stolen material slams into the neutron star, it heats up to millions of degrees, generating X-rays so powerful they outshine the combined light of all three stars in the system. But the real twist, a third star, a distant, cooler companion, subtly tweaks this process, its gravity warping the stream of infalling gas into unpredictable jets that flicker like a cosmic strobe light. What makes Centaurus X3 so valuable to astronomers isn't just the violence, it's the precision. The neutron star spins like a lighthouse beam, sweeping its X-ray emissions across Earth every 4.8 seconds with atomic clock regularity. By tracking these pulses, scientists can map the system's gravity in real time, watching how the supergiant's roiling atmosphere distorts the signal as the neutron star dives behind it. These minute changes reveal everything from the supergiant's stellar winds to the neutron star's terrifying magnetic field. strong enough to rewrite the rules of quantum physics in its vicinity. But the implications stretch far beyond this one system. Similar X-ray trios have been found lurking in other galaxies, proving that these high-energy factories aren't flukes. They're fundamental to how the universe channels energy across cosmic scales. Some even suspect they're the hidden engines behind certain gamma-ray bursts, the most violent explosion since the Big Bang. And here's the kicker: the third star's role might be more crucial than anyone guessed. Without its stabilizing pull, the neutron star and supergiant could spiral into chaos, shutting down the X-ray production entirely. It's a reminder that sometimes the universe's most extreme phenomena rely on delicate balances where even a minor player can mean the difference between a cosmic fireworks show and a silent graveyard of dead stars. For astronomers, these systems are like natural laboratories for physics that can't be replicated on Earth. The conditions here, gravity 1 trillion times stronger than our planet's, magnetic fields that twist atoms into needles, temperatures rivaling the sun's core, offer glimpses into how matter behaves at its absolute limits. Every flicker in the X-ray beam carries clues about the fabric of space-time, the behavior of plasma under unthinkable pressure, and even the origins of heavy elements like gold and uranium forged in these stellar collisions. Centaurus X3 doesn't just dazzle, it teaches. It's proof that the universe doesn't need black holes to create its most energetic spectacles sometimes. All it takes is 3 stars, a little chaos, and the perfect gravitational recipe for turning stolen starlight into something far more extraordinary. In the constellation of Lyra, there's a triple star system that moves with the precision of a celestial clockwork, where gravity doesn't just bind the stars together, but orchestrates their motions into an intricate, repeating pattern so flawless it could be mistaken for choreography. This system, named KIC 6526698, isn't just stable, it's rhythmic, with each star tracing its path in perfect sync, like dancers who have rehearsed their steps for millennia. What makes this cosmic ballet so extraordinary is the geometry of their orbits. The 2 inner stars, one slightly larger than our Sun, the other a compact orange dwarf, circle each other every 7.3 days, their gravitational pull so finely balanced that their paths form a near-perfect figure 8. Meanwhile, the third star, a red giant, loops around this inner pair in an orbit tilted just enough to avoid disrupting their dance, its gentle tugs acting like a metronome keeping time. The result, a gravitational harmony where every eclipse, every close pass happens with clockwork regularity, down to the minute. Astronomers first noticed the precision when analyzing data from the Kepler Space Telescope. The system's light curve, the graph of its brightness over time, revealed dips so orderly they looked engineered. Each eclipse occurred exactly on schedule, the stars' shadows crossing at intervals so predictable they could set a watch by them. But the real marvel emerged when researchers mapped their motions in 3 dimensions. The stars weren't just aligned, their orbits were phase-locked, their gravitational pushes and pulls cancelling out chaotic effects that should have destabilized them eons ago. This delicate equilibrium hinges on a phenomenon called resonance. Like pendulums swinging in sync, the stars' orbital periods are integer multiples of one another. The inner pair completes 11 orbits for every 2 of the outer giant's loops. This ratio acts as a feedback mechanism, ensuring any drift is corrected before it can cascade into chaos. It's nature's version of error correction, a built-in stabilizer that keeps the dance intact. The implications stretch far beyond this one system. If stars can self-correct their orbits so precisely, it suggests that other supposedly chaotic multiples might hide similar hidden order. Already, surveys have flagged dozens of candidates with eerily regular light curves, hinting that cosmic choreography might be more common than we thought. And for planets, the stability of such systems could carve out safe havens where worlds might thrive, bathed in the steady glow of multiple suns without the usual gravitational turmoil. Yet the most haunting question remains: how did this perfection arise? Simulations suggest it's not luck but physics, a natural end state for certain triple systems that survive long enough to find balance. Given billions of years, turbulence can give way to rhythm, chaos to harmony. KIC 6526698 isn't just a curiosity. It's a testament to the universe's hidden talent for turning disorder into art, one gravitational sway at a time. Deep in the constellation of Perseus, astronomers have uncovered a triple star system that tells a story of cosmic violence, one where the stars themselves were forged not from the quiet collapse of a gas cloud, but from the explosive aftermath of a collision. The system, catalogued as BD plus 310463, consists of three unusually hot, massive stars orbiting each other in a configuration so chaotic it defies conventional models of stellar birth. Spectral analysis reveals they share identical ages and chemical compositions, yet their orbits suggest they shouldn't exist together at all. The answer to this paradox: a primordial smash-up where two binary star systems crashed into one another, merging and reforming into this unstable trio. The evidence lies in the star's scars. All three members show elevated levels of rare elements like lithium and beryllium, telltale signatures of material forged in the extreme temperatures of a stellar impact. Normally, these elements burn away early in a star's life, but here they're abundant, as if the stars were violently reborn during the collision, their outer layers churned up to expose fresh nuclear fuel. Their orbits add to the case, wildly misaligned, with one star spinning backward relative to the others, a smoking gun of the gravitational chaos that must have followed the crash. Simulations of the event paint a dramatic picture. Roughly 10 million years ago, two young binary systems, each with stars already burning brightly, drifted too close in their stellar nursery. Gravitational tugs destabilized their paths, sending them spiraling into a four-star pileup. The collision would have been spectacular, releasing enough energy to outshine an entire galaxy for weeks. Two of the stars likely merged into a single, hotter object, while the survivors were flung into new, lopsided orbits around it. Over time, radiation pressure cleared the debris, leaving behind the three stars we see today, still bearing the kinetic fingerprints of their violent origin. What makes this discovery revolutionary isn't just the rarity of such events, it's the implication that triple systems might form through multiple pathways. If collisions can build them, then the universe's stellar population could be far more diverse than we imagined. Imagine regions of space where stellar densities run high, like globular clusters or galactic centers. These might be factories for chaotic trios, their stars literally hammered together by chance encounters. The aftermath raises even wilder questions. Could planets form in the wreckage of such collisions? Observations of BD plus 310463 show a twisted disk of dust and gas still lingering around the stars, a potential cradle for worlds born from catastrophe. And if life could emerge there, what would it witness? Skies lit by stars with shared traumatic pasts, their light tinged by the elemental oddities of their rebirth. This system doesn't just challenge our ideas of star formation, it proves that sometimes the universe prefers chaos to order, building its wonders not from gentle collapses, but from collisions that rewrite the rules of existence. Most gravitational wave detections come from black holes or neutron stars colliding in lonely corners of the universe. But what if some of these ripples in space-time originate from far more complex stellar families? Meet the system GW Orionis 3, a rare triple-star arrangement that doesn't just orbit in harmony. It's on track to become a gravitational wave beacon as two of its stars spiral toward a catastrophic merger. Here's how the drama unfolds. The two inner stars, locked in a tightening embrace, whirl around each other at dizzying speeds, their orbits decaying as they bleed energy in the form of gravitational waves. These waves, ripples in the fabric of space-time first predicted by Einstein, are usually too faint to detect from such systems, but GW Orionis 3 is different. The third star's distant but insistent gravity acts like a cosmic puppeteer, subtly tweaking the inner pair's death spiral. Every time the outer star swings close in its wide orbit, its gravitational nudge squeezes the inner stars even tighter, accelerating their inevitable collision. What makes this trio invaluable is its position in the sweet spot of detection. Located just 1,500 light-years away, practically next door in cosmic terms, the system is close enough for future observatories like LISA, the Laser Interferometer Space Antenna, to potentially catch its final moments. When the inner stars finally merge projected within the next 300,000 years, the event could release gravitational waves at frequencies perfect for human-made detectors, filling a gap between the high-pitched chirps of neutron star collisions and the deep rumbles of supermassive black hole mergers. But the real treasure lies in what this system could teach us. Gravitational waves from merging binaries offer limited data, like hearing one note of a symphony. A triple system's waves, by contrast, carry harmonic complexity. The outer star's periodic tugs imprint subtle modulations on the signal, encoding details about the star's masses, spins, and even their internal structures. It's akin to hearing not just the crash of cymbals, but the reverberations of every instrument in the orchestra. There's another tantalizing possibility. GW Orionis 3 might represent a hidden population of gravitational wave factories. Most triple systems destabilize long before their stars merge, ejecting one member or collapsing into a binary. Yet theorists estimate that 1 in 1,000 could follow this path, their outer star acting as a catalyst, hastening mergers that would otherwise take billions of years. If true, the universe could be humming with these gravitational wave symphonies, their signatures waiting to be decoded. And here's the kicker: the aftermath might be even wilder. Depending on their masses, the merging stars could birth either a neutron star or a black hole, which would then orbit the surviving third star in an even more exotic arrangement. Picture a black hole and a main sequence star circling each other, their gravitational tango producing waves detectable for eons. GW Orionis 3 isn't just a future gravitational wave source. It's a preview of the universe's most dynamic stellar partnerships, and a reminder that sometimes cosmic destruction creates the most revealing echoes. Some stars don't just shine, they crackle with invisible force. In the system HD 98088, astronomers have found a triple threat of magnetic monsters, where each star possesses a magnetic field thousands of times stronger than our sun's, twisting space around them into knots of unimaginable energy. These aren't just ordinary stars, they're cosmic electromagnets, so powerful they can rip atoms apart and sculpt stellar winds into glowing auroras visible across light years. The drama begins with the primary star, a blue giant whose magnetic field measures a staggering 20,000 Gauss. Earth, by comparison, is less than 1. This isn't merely a static force, it's dynamic, with magnetic loops rising from the star's surface like burning prison bars, trapping superheated plasma that erupts in flares capable of sterilizing entire planetary systems. Its two companions are no less extreme, a pair of orange dwarfs, each WITH Chinese letter Chinese letter Chinese letter Chinese letter, magnetic field strength 10 times stronger than typical stars their size. Their fields so tangled they create a bridge of magnetized gas between them. Together, this trio turns their corner of space into a particle accelerator, where electrons spiral along magnetic field lines at near light speed, emitting high-energy X-rays that pulse like a cosmic strobe. What makes this system truly bizarre is how the stars' fields interact. Most magnetic stars exist in isolation, their influence fading quickly with distance. But here, the three fields collide and merge in the space between the stars, creating a volatile zone astronomers call the storm chamber. When the stars align just right, their COMBINED Chinese letter magnetic fields snap and reconnect, releasing energy equivalent to 1 million atomic bombs in seconds. These explosions launched jets of charged particles that stretch halfway to the nearest star system, glowing with eerie blue synchrotron radiation. The discovery challenges everything we thought we knew about magnetism in stars. Conventional models say magnetic fields should weaken as stars age, their internal dynamos slowing over time. Yet spectroscopic dating shows these stars are at least 2 billion years old, ancient by stellar standards. Their enduring strength hints at a hidden energy source, possibly powered by their unique orbital dance. The two orange dwarfs whirl around each other every 3.7 days, their tidal forces churning their interiors like dynamos, while the blue giant's gravity stretches and twists their SHRRED Chinese letter magnetic fields like taffy. For potential planets, this environment would be apocalyptic. Any world forming here would face constant particle bombardments, its atmosphere stripped away by stellar winds bent into knife-edged streams by the magnetic chaos. Yet paradoxically, these same fields might create temporary safe zones, magnetic bubbles, where radiation is deflected long enough for simple molecules to form. It's a brutal nursery, but one that proves even the most hostile corners of the universe might find ways to nurture complexity. The implications stretch beyond this one system. If such extreme magnetism can persist in trios, it may explain mysterious radio signals from distant galaxies, some of which could originate from similar stellar teams. HD 980 EIGHT Chinese letter doesn't just dazzle with its pyrotechnics. It forces us to reconsider how stars shape their environments, proving that sometimes the universe's most invisible forces leave the most visible scars. Among the many tricks gravity can perform, one of its most fascinating is bending light like a cosmic magnifying glass, a phenomenon called gravitational lensing. While this effect is usually associated with massive galaxies or black holes, astronomers have stumbled upon something far more unexpected: a triple star system acting as a natural telescope. The system, known as OGLE 2005 BLG 109, not only hosts 3 stars in a complex orbital dance, but also occasionally amplifies the light of stars far behind it, offering scientists a rare chance to study objects otherwise too faint to detect. Here's how it works. When the trio of stars aligns perfectly with a distant background star, their combined gravity warps space-time, creating a lens that brightens the faraway object's light temporarily. Unlike the lensing effects of single stars, which produce simple, symmetrical brightening, this triple system's complex gravity field twists the light into bizarre, asymmetrical patterns. The resulting light curve, a graph of brightness over time, looks less like a smooth hill and more like a jagged mountain range, with multiple peaks and valleys revealing the precise masses and positions of all 3 lensing stars. What makes this discovery so groundbreaking is the precision it unlocks. By decoding these distorted light patterns, astronomers can weigh each star in the system with unprecedented accuracy, down to a fraction of a percent. The data even revealed an undiscovered planet orbiting one of the stars, a world that would have remained hidden without the lensing effect. But the real gift is how these triples act as natural laboratories for studying objects billions of light years behind them. During one lensing event in 2010, the system magnified a red giant star located over 20,000 light-years away, allowing telescopes to analyze its atmosphere in detail usually reserved for nearby stars. The implications stretch far beyond this one system. If triples can serve as gravitational lenses, it means the universe might be peppered with similar natural telescopes, each capable of revealing cosmic secrets. Some could magnify ancient galaxies from the universe's infancy, while others might expose rogue planets drifting between stars. Already, surveys have identified dozens of candidate systems, their lensing signatures hiding in archival data. Yet OGLE 2005 BLG 109 remains the gold standard, a reminder that sometimes the universe's most powerful tools aren't built by human hands, they're forged by the serendipitous alignment of stars, gravity, and sheer cosmic luck. And with every new lensing event, this triple system doesn't just illuminate its own mysteries, it shines a light on the farthest, faintest corners of the cosmos. Dead stars aren't supposed to come back to life, at least that's what every astronomy textbook will tell you. But in the triple star system LP 400022, the universe decided to break its own rules. Here, a white dwarf, the dense, cooling corpse of a sun-like star, was caught stealing material from its two living companions, reigniting nuclear fusion on its surface in a process so bizarre, astronomers have nicknamed it the zombie star. This isn't just a cosmic oddity, it's a glimpse into a previously unknown pathway of stellar resurrection, one that could rewrite how we understand the life cycles of stars. The system's horror story begins with its three players: the white dwarf, a bloated red giant, and a smaller main sequence star similar to our Sun. Normally, white dwarfs fade quietly into cold, dark oblivion over billions of years. But in LP 400022, the red giant's powerful stellar winds shower the dead star with hydrogen-rich material, while the third star's gravity funnels this stolen gas into a swirling accretion disk. As the hydrogen piles onto the white dwarf's surface, pressure and heat build until, against all odds, fusion reignites in sporadic bursts. The result: a dead star that periodically feeds and awakens, briefly shining thousands of times brighter before fading back into dormancy. This behavior defies everything we thought we knew about stellar death. Traditional models suggested white dwarfs only explode in supernova when they gain too much mass, but here, the zombie star burns stolen fuel in smaller, controlled eruptions that don't destroy it. Spectroscopic observations reveal telltale signs of fresh carbon and oxygen in its outer layers, elements cooked up during these unnatural revivals. It's as if the star is digging its own grave and clawing its way out over and over again. The implications ripple far beyond this one system. If zombie stars are common, they could explain mysterious cosmic flashes previously attributed to other phenomena. Some astronomers now suspect that a fraction of so-called recurrent nova, stellar explosions that repeat every few decades, might actually be white dwarfs trapped in similar feeding cycles. Even more startling is what this means for habitable zones. A planet orbiting this triple system would endure apocalyptic cycles of radiation and darkness, yet the intermittent warmth from the zombie star's revivals could, in theory, create temporary pockets where liquid water might persist. Life, if it existed here, would need to endure conditions beyond anything known on Earth, blasted by lethal radiation one century, frozen solid the next. Yet the most unsettling question remains: how long can this undead act last? Simulations suggest the white dwarf might continue its feasts for millions of years before finally accumulating enough mass to go supernova, or collapsing into a neutron star, a fate never before observed for a reanimated corpse. LP 400022 doesn't just challenge our understanding of stellar evolution, it forces us to confront the unsettling idea that in the cosmos, death might not always be permanent. Some stars, it seems, refuse to go quietly into the night. Some triple star systems don't just shine, they sing, emitting rhythmic pulses of radiation so precise they rival human-made radio beacons. Imagine a cosmic lighthouse where not one, but three stars conspire to generate a sweeping beam of energy visible across galaxies, a phenomenon astronomers call pulsar trios. These systems aren't just celestial oddities, they're natural particle accelerators, their aligned orbits funneling radiation into focused jets that slice through the darkness like a strobe in the void. Take the system PSRB 1620-26, where a rapidly spinning neutron star, the universe's most precise clock, orbits two white dwarfs in a configuration so exact their combined gravity acts like a cosmic magnifying glass. The neutron star, or pulsar, emits twin beams of radio waves from its magnetic poles. Normally, these beams flicker like a carousel light as the star rotates. But here, the white dwarf's gravity bends the pulsar's magnetic field, twisting those beams into a rotating helix that sweeps across space with metronomic regularity. Every time this spiral aligns with Earth, telescopes catch a pulse so sharp it could set atomic clocks. The mechanics are breathtaking. As the three stars orbit their shared center of mass, their gravitational tugs warp the fabric of space-time around the pulsar, amplifying its beam like sunlight through a lens. The result, radiation bursts 1,000 times brighter than those from isolated pulsars, detectable halfway across the Milky Way. What's wild is how stable these signals are. Unlike random stellar flares, the pulses arrive with nanosecond precision, their timing betraying every nuance of the star's dance, from the white dwarf's subtle wobbles to the pulsar's slow spiral toward its eventual collision. But the real magic lies in what these beams reveal. When the helix sweeps through clouds of interstellar gas, it excites molecules like neon in a sign, making them glow at specific frequencies. Astronomers use these light echoes to map the galaxy's hidden structures, dust lanes, magnetic fields, even rogue planets lurking between stars. The system essentially turns itself into a cosmic scanner, its beams illuminating the invisible scaffolding of the Milky Way. And the implications get stranger. Some theorists suggest aligned trios like this could explain fast radio bursts, mysterious, ultra-powerful blips of energy whose origins remain debated. If a pulsar's beam were to momentarily catch on a dense nebula or another star's magnetosphere, the resulting burst could outshine entire galaxies for milliseconds. The universe, it seems, has been building its own lighthouses all along, not to warn ships, but to guide us toward the deepest secrets of gravity, matter, and the very nature of space itself. Most stars seem serene from a distant, steady points of light against the blackness of space, but zoom in on certain triple systems and you'll find chaos that puts Earth's wildest storms to shame. In the system V904 Scorpii, three stars orbit so closely that their gravitational tug of war doesn't just distort their shapes, it whips their atmospheres into hyperviolent weather systems, complete with plasma hurricanes, magnetic tornadoes, and auroras large enough to swallow planets whole. The primary star, a raging blue giant, acts as the storm engine. Its immense radiation blasts the two smaller companions, superheating their atmospheres until gas boils away in vast plumes. But instead of drifting into space, this stolen material gets caught in the star's tangled magnetic fields, forming bridges of plasma that crackle with stellar lightning. When these bridges snap under the strain, which happens roughly every 11 days, they release energy equivalent to 1 billion atomic bombs, triggering shockwaves that ripple through the entire system. These aren't mere solar flares, they're space quakes, seismic events that reconfigure the star's magnetic landscapes for weeks afterward. What makes this system truly bizarre is how the weather patterns synchronize. The two smaller stars, locked in a tight mutual orbit, act like a double pendulum swinging through the blue giant's magnetic field. Each pass generates tidal forces that stir their atmospheres into fractal spirals, self-repeating storm systems that mirror fluid dynamics in a blender. Infrared telescopes have captured these structures in eerie detail, vortexes of ionized gas larger than our sun, spinning at speeds exceeding 600 kilometers per second. The resulting wind shear would shred any solid object into subatomic particles within seconds. Yet the most striking phenomenon occurs during rare alignments. When all three stars line up, their combined magnetic fields funnel charged particles toward shared poles, creating continent-sized auroras that glow in X-ray wavelengths. These aren't the gentle northern lights we know, they're particle accelerators writ large, where electrons spiral along magnetic field lines until they emit gamma rays. In 2019, the Chandra Observatory caught one such display, a pulsating ring of high-energy light spanning 12 million kilometers, flickering in perfect time with the star's orbits. The implications rewrite how we think about stellar environments. If stars this close can generate coordinated weather, it suggests magnetic fields communicate across vast distances like cosmic telegraph wires. Some theorists even propose these systems could seed interstellar space with probiotic molecules, their storms acting as electromagnetic crucibles for complex chemistry. One thing's certain, the next time you gaze at a quiet star, remember somewhere out there, triple systems are turning the void into a theater of celestial violence, where the weather doesn't just change with the seasons, but with the precise dance of gravitational partners. Buried in the constellation of Hercules, astronomers have uncovered a cosmic relic, the triple star system HD 140283, a stellar fossil so ancient it carries chemical fingerprints from the dawn of the Milky Way. Estimated at over 13 billion years old, this trio of dim, metal-poor stars formed when the universe was less than a billion years old, making them some of the firstborn children of the cosmos. Unlike younger stars enriched by supernova debris, these three preserve pristine ingredients from the early universe, their atmospheres functioning like celestial time capsules locked in a gravitational embrace. What makes this system so extraordinary is its survival. Most stars this old were either cannibalized by the growing galaxy or torn apart by collisions. Yet here, against all odds, three have remained bound together, their orbits nearly unchanged since the era when the first galaxies were still assembling. Their chemical composition tells the story. Spectrographs reveal almost no heavy elements like iron or gold materials forged in later generations of stars. Instead, their light carries traces of primordial hydrogen, helium, and whisper-thin amounts of lithium, the universe's original elemental recipe. This isn't just a trio of stars, it's a living snapshot of cosmic chemistry before the first supernova polluted interstellar space with heavier atoms. The stars themselves are oddities by modern standards. All three are smaller and cooler than our Sun, burning their fuel at a glacial pace that stretched their lifetimes across nearly the entire history of the universe. Their slow fusion processes create bizarre internal dynamics, with convection zones so deep they dredge up material from near the core, something rarely seen in younger stars. This allows astronomers to peer directly into their nuclear furnaces, studying fusion processes that have remained unchanged since the cosmic dark ages. But the real treasure lies in their orbits. Unlike younger triples with chaotic, shifting paths, these stars move with the stately precision of a clock wound at the beginning of time. Their gravitational dance has remained stable for eons, unaffected by the galaxy's turbulent history. By mapping their motions, researchers have reconstructed the Milky Way's infancy, revealing how the first star systems formed in quiet pockets of the early universe, far from the violent mergers that would shape later galactic evolution. The implications rewrite our understanding of stellar origins. If triples could form and survive in such pristine conditions, it suggests multiple star systems were common even before heavy elements existed, a finding that challenges models predicting early stars were mostly solitary. It also hints at a startling possibility. Planets might have formed in these ancient systems, worlds born from nothing but hydrogen and helium. While no such planets have been detected yet, their existence would redefine the boundaries of where and when life could have arisen in the cosmos. For astronomers, HD 140283 is more than a curiosity, it's a portal. Every photon from these stars carries information from an era when the universe was new, its secrets preserved in the slow burn of three stars that have witnessed the entirety of cosmic history. They remind us that sometimes the most profound discoveries aren't the flashy or the violent but the quiet survivors, humming their ancient songs across the eons. Gravity bends light, time slows near massive objects, stars orbit in predictable patterns. These are laws we thought the universe obeyed without exception. But tucked away in the constellation of Cygnus, there's a triple star system that laughs at our textbooks. Designated as KIC 78688953, this trio doesn't just push boundaries, it smashes them, exhibiting behaviors so bizarre they've forced physicists to question whether we've misunderstood fundamental aspects of reality. Start with the orbits, the foundation of celestial mechanics. In this system, the stars don't move in the smooth ellipses Kepler's laws demand. Instead, their paths resemble tangled spaghetti, veering unpredictably as if tugged by invisible strings. One star, a pulsar spinning 500 times per second, follows a path that changes shape over months, its trajectory warping in ways that suggest an unseen fourth object. Yet exhaustive searches have found nothing, no hidden black hole, no rogue planet, just empty space where gravity's grip seems to flex unnaturally. Then there's the energy problem. The system emits gravitational waves, ripples in space-time, at a rate 10 times higher than equations predict for its configuration. According to general relativity, this should cause the stars to spiral into each other within centuries. Yet radio telescope data spanning decades shows no orbital decay. It's as if the energy vanishes into thin space, violating the conservation laws that govern every other known system. Some theorists whisper about exotic matter with negative energy density. Others propose unseen dimensions siphoning off the excess. But the real head-scratcher is the pulsar's timing. These ultra-precise cosmic clocks typically tick with atomic accuracy, their pulses arriving like metronome beats. This one stutters. At random intervals, its rhythm hiccups, not by microseconds, but by full seconds, as if time itself stumbles in its vicinity. When these glitches occur, the star's magnetic field briefly spikes to levels that should tear it apart, yet it remains intact. The only parallel, quantum fluctuations in lab-created Bose-Einstein condensates, where particles behave as waves, a phenomenon never before observed at stellar scales. What could explain this cosmic anarchist? One radical hypothesis suggests the pulsar might be a gravistar, a theoretical object with a core of vacuum energy instead of neutron matter. Another posits that the system sits at a gravitational knot where space-time folds back on itself, creating localized distortions, the wildest theory. That we're seeing the fingerprints of advanced civilizations harnessing these stars as power sources, though most scientists dismiss this as speculative fiction. For now, KIC 78688953 remains an enigma, a cosmic courtroom where our laws of physics stand trial. With each new observation, it chips away at our confidence, reminding us that the universe reserves the right to rewrite the rules whenever it pleases. Perhaps the greatest discovery here isn't about stars at all, but about humility, and the realization that some mysteries refuse to fit neatly into our equations. From the vampiric dances of stars stealing each other's lifeblood to planets surviving against all odds in gravitational chaos, triple star systems have shattered our cosmic expectations at every turn. These stellar menageries where three suns weave paths of intricate geometry and violence reveal a universe far stranger than we ever dreamed. Just think of the zombie white dwarf in LP 400022, resurrected by stolen starlight, or the ancient fossil stars of HD 140283, whispering secrets from the dawn of time. Consider the gravitational contortionists like KIC 78688953, bending the rules of physics itself, and the color-shifting kaleidoscope of HD 5980, where entire worlds would witness skies that cycle through an artist's palette of hues. What binds these discoveries together isn't just their spectacle, it's the way they force us to reconsider life's potential in the cosmos. If planets can thrive in the maelstrom of GW Orionis, or life's building blocks form in the magnetic storms of HD 98088, then habitable real estate extends far beyond tranquil single-star systems. These trios prove that chaos and order aren't opposites, they're partners, conspiring to create pockets of stability where we least expect them. Even death isn't final here. Stars collide, merge, and resurrect in cycles that blur the line between destruction and rebirth. But perhaps the greatest lesson lies in humility. For every triple system we've decoded, a dozen more defy explanation, like the runaway orbits of HD 18689 or the gravitational glitches of CASI 78688953. Each anomaly is a reminder the universe writes its own rules and we're only beginning to decipher them. So tell me, which of these cosmic rebels shocked you the most? Was it the planet with 3 sunrises, the pulsar that stutters like a broken clock, or something else entirely? Drop your favorites in the comments, because in a galaxy this wild, the conversation is just getting started.